Hello everyone, my name is Toshiyuki Shimizu. I'd like to introduce Fujitsu, Supercomputer Fugaku development collaborating with RIKEN. So today I talk about the Fugaku project, the Fugaku supercomputers development project overview. Then I'll talk about our co-design with RIKEN and application developing teams briefly. And thirdly, I'll review the results of co-design using the Green 500 and open source software applications and Fugaku priority issues. Let's get started. As you know, supercomputer Fugaku is a successor to K computers. The goal of the development of supercomputer Fugaku is high application performance and good power efficiency and good usability. These three important goals is goals of the Fugaku development. In order to attain these goals, we utilize these approaches. For application performance, we work with application developers or researchers through the co-design approaches. And we developed Fujitsu original CPU cores for application performance and support high memory bandwidth memory or HBM2. For good power efficiency, we use leading-edge silicon technologies and our proven high performance and low power logic designs. And we also support power controlling knobs. For good usability, we decided to use ARM instruction set architecture. The K computer uses Spark instruction set architecture. That was good, but unfortunately, the user is very limited. Spark Linux is only supported by Fujitsu. So we decided to encourage the customer or users to use ARM binaries can run on the Fugaku also. There is many platforms running on the ARM Linux binaries, so we will support to run that binaries. So also we developed, we support ARM leading edge instruction extension for high performance servers, known as scalable vector extension. SVE is developed by ARM, but Fujitsu also collaborated with ARM as a lead partner. So by using so, we believe that the supercomputer Fugaku will be good application performance and good power efficiency and good usability. This is a development schedule of Fugaku project. So at the early stages, application for Fugaku is selected, application review, and during the feasibility studies, many architectures, including vector and accelerations, and a cluster of general purpose CPU is studied. So that evaluation is done, and cluster of general purpose CPU is selected as a system architecture for the supercomputer Fugaku. Then we started the development of the supercomputer Fugaku as the basic design and detailed design. During this phase, we work with application developers to evaluate the system and performance. So now we are installing the Fugaku system at the Here, Fugaku facility, RIKEN facilities now. You may saw the facility last night. Okay, and we talked about the Fugaku co-design approaches. As I said, the goal of the supercomputer Fugaku is high application performance, 100 times application performance than K computer, and should be the power budget limit requirement, so 30 or 40 megawatts. We optimize applications and compilers and libraries and hardware itself. So we should attain these goals by doing everything. So co-design approach is very simple. First, evaluate the design and optimize the design. For the evaluated design, we use three parts of the performance. One is computation, and the other is communication and I/O times. Application has 3 parts of time. Cost should be evaluated. So we use application information and performance count of the Fujitsu previous commercial supercomputer FX100, and also uses cycle-based simulator of Fugaku. For communication time estimation, we use bandwidth and latency and communication pattern of the communication. Then we optimize the application and compilers and libraries and hardware to resolve the bottlenecks. So estimation environment or tools is as follows. We have precise performance estimation tools. So we apply these tools for the primary kernel. And this we make the Fugaku object and run them on the Fugaku simulation, cycle-based simulation. It is a very informative result we can get to optimize, but takes time. So other part or other section of application is evaluated by another estimation tools. So brief performance estimation tools. So we correct the performance counts by running on our previous commercial supercomputer FX100 and replace the counts with Fugaku architecture parameters. By using this, we can get brief performance estimation quickly. For power consumption estimation, so we use more precise evaluation using the very simple kernel like VGM. So we run these small kernels on the emulators, so and correct the totals of logics and estimate the power consumption. Also, the memories are estimated or interconnect power consumption is also evaluated. So during this work, so we optimize Fugaku systems. So the co-design work is very busy around 2015 to finalize system architecture or parameters. So we work to surround the cycles of this optimization. So define and refine a set of architecture parameters and implement or tune the kernel, application kernel under the architecture parameters, and evaluate the execution time using the estimation tools. So we have several tools for estimation of performance and power. So we identify the hardware bottlenecks and explore design spaces. So this turnaround or cycles is done weekly or bi-weekly. So we are very busy around 2015. So by using this, we define these architectural parameters, CPU frequency and number of cores. This architecture parameter is defined by using these iterations. So, and as I said that we changed the ISA from SPARC to ARM. So our SPARC processor has 128 general registers. However, ARM has only have 32 registers. So we need to understand the differences of effects of the differences. So we also evaluated this difference using this kind of evaluation cycles. And we need to enhance our compilers to support, to compensate the differences of architectures. Memory and interconnect parameters are also studied. And architectural, implementation of microarchitecture of instruction is also studied. So such as combined gather instruction is improved during this evaluation stages. So after these cycles, finally, we finalize the Fugaku CPU architecture parameters or specification. We use ARM SPE and performance of the tip of double operation performance would be the 2.7 teraflops per chip. So, and Fugaku CPU support frequency is 2.0 gigahertz. So the performance will be 3.0 teraflops per chip. User can specify or boost the CPU frequency up to 2.2 gigahertz. So the for Fugaku, if the power consumption budget is supported. Okay. So, and memory bandwidth is 1028 gigabytes per second. So we also integrate the interconnect into the chip. This is a specification of A64FX CPU. So hardware implementation of the A64FX, we use leading edge technologies, and we integrated the memories or HBM2 into the chip using CAS technologies. Okay. For the memory bandwidth implementation of the A64FX is also uncompromised memory bandwidth is supported. So from the memory to the execution unit, we support high memory bandwidth. So for application performance. This is an example of the microarchitectural optimization of the data access or data bandwidth. Upper side explain about the load performance of the unaligned data. It is difficult to load unaligned data at the 100% peak performance, but our A64FX allow to load the unaligned data for 100% throughput. The bottom side shows the combined gather. So ordinary CPU need to load the 8 data, indirect data or index data takes for 8 CPU cycles. But A64FX can load 8 index data in 4 CPU cycles if the sum condition is met. This graph shows the power knob to reduce the power consumption. So some application or data-intensive application often utilize the logics or execution unit fully. So in that case, we can reduce the activity of the execution unit. So by doing so, we can reduce the power consumption without performance degradation. Some application succeeded to reduce the power consumption without performance degradation. So this is a Fugaku system software stack. Green part is developed by RIKEN, and the others are developed by Fujitsu. Fujitsu compiler support A64FX featured fully and optimized to run the application. And also, management software support the A64FX, the power knob capability, and also utilizes assistant core for application performance. Okay. We will show to the performance and energy consumption using the Green 500 and other applications. Last supercomputer, we received A64FX prototype or Fugaku prototype received #1 places. So this is this shows good power efficiency of the A64FX or Fugaku. The point is a combination of hardware and software optimization. Hardware side, A64FX is designed for energy efficiency. Fujitsu proven CPU microarchitecture and leading-edge silicon technologies. And TOP500 interconnect is integrated into the CPU chip, and memory is also integrated into the packages using CAS technologies. So only the CPU packages are required to build the Fugaku system. Other components are consuming the power is not required. So, and for the software side, math libraries are already tuned for application performance, and communication libraries are also tuned utilizing the Fujitsu, long experience of TOP500 interconnect. So K-computer uses TOP500 interconnect also. And performance tuning is efficiently done utilizing rich performance analyzer and monitors. So we succeeded in this environment to receive the first place of the Green 500. Okay. So I will show how good the performance efficiency of the A64FX. HPL or RIMPAC is easier for the large data set or program size. But our prototype is very limited of the data sizes or programs. So, however, we can achieve good efficiency like the 84.75% with small data. This is because optimized communication and math libraries and overall communication of the calculation and communication. Okay. This is the result of the open source software applications. We evaluate these applications using the latest x86 latest x86 CPU, 2 socket, and 1 socket of A64FX. As you see, we can achieve up to 1.8 times faster than x86 CPU. So this is because these applications are good for the high memory boundaries. And A64FX wide SIMD is very effectively utilized. Okay. This shows the power consumption evaluation or energy evaluation for the same applications and same conditions. You can see that 3.7 times better than x86 processors. So we can say that the high power or energy efficiency is achieved by our energy conscious design of A64FX. Okay. This table shows the Fugaku priority issues. This table is posted on the RIKEN portal site, and you can see that this estimation shows that some applications exceed 100 times performance of the K computers. So, and this application power consumption is also met the requirement of the Fugaku supercomputers. Some applications utilizes power knobs to reduce power consumption and achieve high energy efficiency. Now we are measuring the optimizing using real hardware. Okay. So we'd like to evaluate how the estimation of power performance and power is. So you can see that the two points are around 2018 and 2020. So the 1.5 years before, we evaluate the performance and power without hardware. And now we add the real hardware result. So this graph shows the performance and energy consumption normalized by previous estimation. So around 2018. Okay. So for the performance larger than 1 means the current performance is faster than previous estimation. For the energy smaller than 1 means the power consumption in the current estimation is lower than previous estimation. A and EF is a Fugaku priority issue. So we see that the simple benchmark kernels like DGM and streams performance are matched due to the precious simulation. For power consumption, or energy consumption. The error is 8% in logic DGM and 15% in memory or stream. I think that this variation or error is acceptable for design or power estimation. Okay. Application A, B, and C. So this is performance is good, better, improved, and energy is reduced. So I can say that the computation was reduced after the previous estimation. So this is a good news for application performance and energy consumption. Last group, D, F, D, E, and F is good estimation and optimization. Errors are around less than 20%. So this is also good for the co-design approach. This shows the optimization direction correctly. Okay, I will summarize my presentation. So Fugaku is co-design with application developer and runs application at high performance with optimal power consumption. And our HPC ecosystem and applications portfolio are growing by effort of communities and selection of hardware. Now, Fujitsu provides commercial version of supercomputer FX1000 and 700 based on Fugaku technologies. Cray also provides system utilizing Fujitsu A64FX ARM CPU. I hope the customer or user or researcher can utilize these platforms and get good results. Thank you.